All right, welcome back everybody. This is the last tutorial that we're going to need to use for electric charges and electric fields. So this is a super important one that's going to be really helpful for the next section where we understand this concept with something called Ohm's law and how I can now have running electricity and the relationship between something called charge and voltage. But to give you a little bit of grounding, so to speak, a bit of a play on words there, if you take a look at the most common use of separation of charges where you have a buildup of electrons that will automatically then discharge is in lightning. So if you want to, this is a great link that's found on our D2L notes. Feel free to take a look at this because it actually explains how this works. But essentially, when you see a lightning strike, you have an amazing separation of charge, which is essentially just a lot of electrons moving from one place to another. So if you basically look at how clouds work, you have a difference in sort of dry versus the moisture in the clouds. And so there's going to be sections of the cloud that become positively charged because the electrons move away from that section of the cloud. And remember, if I lose electrons, I become more positive. And then if I have dry ground, again, they become more electrically or negatively charged because they're going to start gathering electrons. So once I have this imbalance, as we all know, positive will flow to negative. Okay, and that's why, again, you will see a lightning strike. Now, the interesting part is when you take a look at this, is that because we know charges work in electric fields, it always goes from positive to negative. So one of the things, if you really wanted to be technical, it actually, lightning always goes from the ground up, if you really wanted to be pedantical about it. But this is just kind of a great introduction. This idea of voltage versus charge. So when you look at a lightning strike, you basically have a massive discharge of electrons. So this idea of charge we have already learned about. We know that charge is in coulombs. And so if you go back to your electric field strength, we have been using this concept all along. And that concept is right here. This is Q. Remember, Q is the charge of the source. And our unit for that has always been in coulombs. So if you actually really want to understand this well, you need to understand that for every 1 coulomb of charge, I can actually count the number of electrons being moved. And it's 6.25 to the 18th. I want you to imagine that number. That is an exceedingly large number. So if I have 2 coulombs, well, you basically have 6.25 times 10 to the 18th times 2. So again, that's just going to multiply. So the higher the coulombs, the more electrons you have moving. So again, I can either gain electrons, which means I'm going to have an overall negative charge, or I can lose electrons, which means I have a positive charge. So again, just make sure that you understand what a coulomb is. If you need to, this is a great video on, again, crash course. Don't worry about the math that she is going to go through near about the 5-minute mark. You just need to understand and can visualize what a coulomb is. And in a way, like if we have a calculation that we now have 1.2 coulombs, you have just over 6.25 to the 18 electrons moving from place to place. And if you realize that, it's going to help a lot. So when we actually take a look at a current, okay, so a current again is in coulombs, okay? This is a connection to that. So a current is where I have those electrons now moving. So a current is the movement of electrons. And so we usually see this in obviously electricity, okay? So if I have an idea about current and if I can measure the number of electrons moving and I now have a unit of time, I now have what's called an ampere or an amp. So you might have heard about this. So the amp is the unit for current. We use capital A, and really all an amp is the number of coulombs that move past a certain point per second. So think of this as, again, this idea of speed. It's not the best way of looking at it, but it really helps you conceptualize it, okay? So if I was looking at, say, moving water, this is literally the amount of water that would pass a given point, okay? So the unit is coulombs per second, and if I looked at it in a formula, I'm going to see the symbol I. So eventually when we start looking at Ohm's law, we're going to come back to this. Again, great video here that is in your D2L notes if you wanted to look at it. Now, with a current, there's also this idea of a voltage. Now, voltage is the amount of push or potential energy that every charge has, okay, or that every coulomb has. So when you take a look at current versus voltage, Current, again, is the number of electrons that are moving past a second. Because remember, for every 1 coulomb, I can actually quantify that now. Okay, and that is 6.25 to the 18th electrons. Okay, so if I now wanted to find out, well, how much push does each of those electrons have in a way, I am looking at a concept of voltage. So again, voltage is, again, this idea of potential energy. Think of it as the push behind each charge. Okay, so if I have a big voltage, every little electron has a big push versus a little voltage would have a little push. And you're noticing that I am using arrows because, again, I can show sort of directionality with this. So I can actually calculate voltage. So if I understand the basics, voltage is the amount of push or the amount of energy, and you've learned about this before, for every 1 coulomb, or think of it for every 6.25 times 10 to the 18 electrons. Okay, so it's how much push those electrons have. So again, think of a falling waterfall. If I have this water that's sort of going over a really, really steep cliff, it's going to have more push or more energy in it. That's why, again, if you look at the way I can calculate this, the amount of energy is on the top per the amount of charge, or again, the number of basically electrons that are going through. So this is going to be super important that you understand the concepts of voltage versus charge. Charge, again, is the amount of electrons that are passing a certain point, and the voltage is the amount of push that they have. If I wanted to calculate voltage, I take the amount of energy I have divided by the charge, or again, what we've just learned about in our last section. Okay, so this is now, again, a really important summary that what's more dangerous, voltage versus charge. Now, any high voltage and high amperage is going to kill you. But on the average, a higher current is more dangerous. Okay, so here's some examples. So if I have a static spark, so basically I've have a discharge of a wool sweater on a rug, you are going to have a high voltage because each of those electrons have a lot of push behind them, but it's a pretty low charge. So you're okay. It's going to hurt, but you'll be fine. Then if I were to say take an electric plug, so this is again is an electrical socket. If I were to stick my finger in those, well, I have a problem because I have a medium voltage. I only have about 240 volts that are coming through, or 240 units of push. So that's kind of a medium push, but I have a tremendously high number of current or electrons running through. This is lethal, and that's why you can have a heart attack if you stick your finger in a plug. And then lightning is a little bit of both, where each of those electrons has a high push and I have lots of them. So at the end of the day, understanding electrical safety is going to save your life. So this is going to be a really important section on how I can break down each of these questions. So if you need to, pause the video, see if you can try these questions on your own, and then let's see if you can solve them. So welcome back after you've just paused this. So this first question is a good one because I've walked across the carpet on a dry day and I've acquired a negative 55, again, microcoulomb charge. So we're going to have to understand how to convert this in just a second. So if I take a look at the questions a little bit at a time, first thing, have I gained or lost electrons? So I know the answer to this because of this part of the question. Right here, I have a negative symbol. So that negative means that I have gained electrons. Okay, so the only way that I can get a negative charge is if I gain those little negative guys. Where did it come from? Well, the electrons came from the carpet. Okay, so I can now say that that carpet is probably positively charged because, again, I have stolen those electrons. Now, how many electrons were gained? Well, this is the fun and games when you look at sort of unit analysis. In the question, I'm first going to take my 55 microcoulombs and I'm going to convert that to coulombs. So in order to do that, again, I'm going to look at my data booklet on page 1, and this idea of a micro is times 10 to the negative 6. So I'm going to write down my original value of 55, and then I'm going to convert it by going negative 6. So that's first job. I need to have the number of coulombs. So remember, 1 coulomb was 6.25 to the 18 electrons. So I'm going to use that, just like we learned how to build time when we did blood pressure and heart rate. I'm now going to multiply this by the relationship I know between the number of electrons and coulombs. So I know, based on just the last slide that we looked at, that for every 1 coulomb, there's a physical number of electrons. and that's 6.25 to the 18 for 1 coulomb. So if I've set this up properly, you'll notice I have a coulomb on the top, a coulomb on the bottom, and now I can find out how many electrons were transferred by simply multiplying 55 to the -6 times 6.25 to the 18. And you are going to get a tremendous amount of electrons. And so you're going to get roughly 3.4 times 10 to the 14 electrons that were gained. Okay, so again, you're going to feel that as a bit of a spark. Okay, now the last question here kind of puts it all together. If I did apparently 0.5 units of work or 0.5 joules of work by scuffing your feet, what's the voltage? So how much push is there behind these charges? Well, if I look at what we've just learned, we know that voltage. If I take the energy, and this is potential energy, you guys. Okay, so that's why we're going to use EP, because that stands for potential energy, because that's what voltage is. It's sort of the push that it could have. And I'm going to divide that by the charge. So this was on our last slide. I would write this in page 2 in your data booklet. It's going to be helpful. And if I look at what I know, my energy is given to me in the question of 0.5 joules, because unit for joules is a J, or energy is J. I know my charge, again, it was up here. We've just figured it out that it was 55 microcoulombs. So I'm going to convert that again to 55 times 10 to the -6 coulombs. That's my charge. So now if I just do 0.5 divided by 55 to the -6, you are going to get 10,000 is the number. And if I look at my units, I have a joule over a coulomb. And that's a joule per coulomb. And this is exactly what a volt is. It's the amount of energy, or the amount of sort of the ability to move something per every unit of charge. So that's kind of cool that we can actually calculate that. So if you need to, pause this video and go back and make sure that you can calculate that on your own. Now, the last question we have here is, again, it's going to require you to take this last concept that we just learned, that voltage is, again, the amount of potential energy over the amount of charge that an object has. But in this particular question, I actually want to know how much energy. So I need to put this equation, I need to rearrange it and put the potential energy in the driver's seat. So if I do my algebra correctly, I should now just be multiplying the voltage times the charge. So once you can do this, and again, if you need help with this, come see me at Focus and I can work you through it. If I then look at everything else, do I know my voltage? Yeah, I know that is 120 volts. It's right here in my question. And I know that my charge is 15 coulombs. So again, it's important you can identify the values. So remember the symbol that's behind your number, this is your unit. Okay, that's what describes what the value is. And the letter you have within the equation is your symbol. This is going to be within your formula. So for some of you, that's going to be a really important identifying feature, is make sure you know how to identify the numbers and what they mean. So eventually, if I put everything together, and I am going to make sure I put in my units just to show you something really neat. If I now do the math, and it's just 120 times 15, that is going to be 1800. And if I look, I have volts per multiplied coulomb. That's what it tells me. Now here's a really cool thing. If I look, I'm being asked to find energy. Now I know that energy, the unit for that is a joule. We've learned about this enough in class. But if I were to take apart a volt, and we learned this on the last slide, I learned that a volt is the same thing as the amount of energy per coulomb. Okay, so if I now were to substitute this in, and I now have 18 instead of the volt, I put a joule per coulomb, and this was multiplied to a coulomb, look what happens. The coulombs will divide out to be 1, and lo and behold, I am left with a J. And this is beautiful because that means I have 1800 joules, and that is exactly the unit I want for energy. So I really hope that helps. Make sure that as we kind of progress through this, you're going to get an exit slip. This is going to be super important for your written section on your assessment that will be coming up. So if you have any questions, please see me.